Okay, looks like we're on our way. Give us about 10 more seconds.
Yeah, I just saw us start to go live there. Amazing. All right, we are in fact live and online. Hey, everybody. Welcome to the Weights and Biases Deep Learning Salon, the final Weights and Biases Deep Learning Salon of the year 2020. The next Weights and Biases Salon will be next month in January, on January 19th. We're going to be switching over to a monthly format rather than a bi-weekly format. And so our January speaker will be Greg Yang of Microsoft Research. Greg has been doing this really awesome work on infinite width neural networks. Big networks are better, right? So why not work with infinitely big networks? So Greg's been working on this approach called tensor programs to try and understand what infinitely big neural networks can and cannot do. And there's been some really exciting developments over the last couple of months, and I'm really excited to hear from Greg on those on that topic. So you can RSVP at that W&B.me/salon link starting in just a few minutes. You can also catch all of our salons on our YouTube channel, including this one and eventually Greg's. If you go to our YouTube channel and check it out, we've got a playlist of all of our deep learning salons. We also we announce things like the salons and other events that we do on YouTube and on Twitter and in our Slack community. So that's the best place to go to know where stuff that's happening with Weights and Biases, to know about it before it's announced elsewhere, and to be able to participate in some of the special things that we do. We're doing a reproducibility challenge associated with NeurIPS, and we're doing a bunch of collaborative model training projects over the next couple of months. So that's all organized via the Slack forum, which you can join at wandb.me/Slack. So that's the Weights and Biases Salon background and our community as a whole. Today, what our salon is going to focus on, we're going to talk about we're going to hear from folks at ML at Berkeley, an undergraduate student organization, about some of the work that they did over this past semester. So we're going to hear from 3 separate teams that worked on 3 different projects, each very different from the other, but all attacking a different subfield in deep learning and machine learning. And I'm really excited to hear from all of them about their work. We're going to start with some folks who worked on what was more of an ML engineering project. So we're going to be hearing from Ashwat and Andre on their design of a computer vision based video gesture overlay for Zoom, which they will, if the demo gods are with us today, demonstrate live as part of the salon. So Andre and Ashwat, take it away.
Awesome. Thank you, Charles. Give me 1 sec. Okay, sweet. And yeah, okay, awesome. So hello and welcome to our presentation, which is Video Gesture Recognition and Overlay. This is a presentation, a final project that we did for the new member education program here at MLab, or Machine Learning at Berkeley. And yeah, we're excited. We hope you enjoyed that presentation. So first and foremost, I want to introduce the team. My name is Ashwat, and I worked with Arya, Andre, and Sarv this semester on this project. Andre will be joining us for the second half of this presentation, and Arya and Sarv will hopefully be online answering questions on the YouTube live stream, as well as at the end to answer questions. So first and foremost, what was the goal of this entire project? Why did we do this? And let me ask you this. How many times this year on Zoom has someone tried to screen share and they asked you the question, the dreaded question, can you see my screen? To which the answer is almost 99% yes. And then you wait this awkward silence until someone finally says, unmutes, they say the one word yes, and then they mute themselves again. We thought to ourselves, like, there's got to be a better way. There's got to be a way to use machine learning to prevent the need to unmute, to just say a quick word like yes, or I have a question, or I have something to say, or goodbye. On top of that, we wanted to make the Zoom equivalent of emoji reacts, because emojis are pretty much like a second language to all of us right now, and all of us know it. So like, how do we combine the 2 things, make it kind of fun? And last but not least, we said, how do we combine some relatively simple concepts to solve a real world problem? In this case, being the convenience on Zoom. So on the right side, you can see a GIF of me where I'm doing a demo of what we created. So I'm gone for a second, I'll be back. But pretty much what I'm trying to do is, you can see my hands will make all these gestures on the camera. and an icon will show up because the camera recognizes what I'm trying to say. So this would be a comment. I believe the next one would be like a goodbye, a peace sign. So yeah, we'll get into detail about that. So now the first step when it comes to trying to do any kind of gesture recognition is to find out where in the frame your hand is in the first place. So for us, we decided to use some off-the-shelf tracking modules. So for hand tracking, we decided to use Victor Debia on GitHub. He had a great GitHub repository about this. And then for face tracking, we decided to use the good old reliable Haar Cascades. So here are some animations showing how this works. On the bottom left is Victor Debia's GitHub. I believe he trained this using transfer learning on MobileNet v2, and definitely was really good. And that was a great foundation. And on the bottom right, we have the Haar Cascades for facial Haar Cascades. And we use both of these as like a foundation to build off of. And then again, we had to take this, kind of modify it up a bit, change the inputs so that we could make it as tailored as possible for our specific ML model, which Andre will talk about in the future slides. So quick detour into how Haar Cascades work. I just want to quickly talk about this. So right off the bat, Haar is the name of a Hungarian mathematician. I believe he came up with something called Haar sequences in mathematics, which led to Haar wavelets. Haar wavelets are intuitively similar to Haar features. And that's where we came here today. So Haar features are pretty much very good at identifying edges and lines in an image. And I think this was proposed by Viola and Jones in the Viola-Jones algorithm in a paper they wrote to CVPR back in 2001, if you know what that is. But overall, what it does is it takes the average of all the pixels in the white region, the average of all the pixels in the black region, subtracts the two means. And if they're around a certain threshold, then you pretty much have a good confidence that this is an edge or a line in the image. Now, the next natural question is, well, there's edges and lines, but how does that apply to my face? Because like everyone's face is different. There's no edges or lines directly in your face. And that's what this diagram shows beautifully. Pretty much your eyes can be captured very well with an edge feature, as shown in this. A nose can be captured and a mouth can be captured with the line features relatively well. So in a sense, these Haar features will kind of map and really reliably map to parts of your face where they'll match up closely because the pixel intensity between the luminosity between, I guess, like your nose and the surroundings. And pretty much that's how it works. And next, an animation showing how this all works together. So what it does is it slides a window across the entire image and it runs these features across every single thing and gets like some kind, how many ever hits it can kind of get. So the next question naturally is, we have thousands of these Haar features and we have so many windows. That's a lot of calculations for a real-time face detector. So how does it work so well? And that's where the cascading parts comes into play. So it's called Haar Cascade because it's a cascade of Haar features. And what it does is pretty much it takes a few low-level core features, runs it across a window in an image. And again, if it doesn't pass the initial features, like if it doesn't pass the test, I guess, in the beginning, there's no reason it would pass the more intricate or detailed test later on. So thus you can discard an image or part of the image right away. And thus at the end, the parts of the image that passed all of these cascading tests will be classified as a face because it kind of like passed all of the cascade of Haar features that I wanted to find. And that's what's returned as a bounding box to the user. Now moving on to gesture classes. So on the left side, you can see all of the like emojis showing what kind of hand gestures we use for these classes. And the middle is the like class that we wanted to identify as. And on the right side is the icon that we wanted to show. So for us, we thought the most core things people want to say that they don't need to unmute for is, I have a question, or, yes, sounds good. You can say, no, please stop. I have something to say, a comment, 1 or 2 fingers, peace sign, like I'm going to go goodbye, end of the call. And last but not least, my personal favorite, and I think one of the most important, is the out of frame. And the reason for this is because I think that many times I've seen this in calls myself at university this past semester, but people would leave their camera, but they leave their video on, which leaves their entire background to the viewer's, pleasure, whatever they may be. And usually it's not a very bad thing because, I hope it's not a bad thing, but oftentimes we've all heard stories of, things going awry when things in your background are being shown. So we thought to ourselves, when someone walks away from the camera, our software will automatically cover up the entire video stream. So it says away from keyboard. And when you walk back into frame, it'll know that you showed back up, and then it'll remove the mask. So thus, this entire process is fully automated. No need to click a button or click a mouse click or a keyboard click. All you got to do is just raise your hands or simply leave the camera, and everything is done completely by itself because it's detecting every step of the way. Now I want to pass the mic off to Andre, and take it away.
Thanks, Ashwat. So for the second part of this project, we want to build a gesture cluster, and our plan was to use a CNN and train on some sort of hand gesture data set. What we found for this is this American Sign Language alphabet data set from Kaggle. It has 29 classes with 3,000 images per class. Now that sounds like a lot of images, but it's actually not in practice because these are frames to a video, meaning adjacent images are almost identical. So to avoid wasting training time on those, we only use every 10th image from the data set. We also do extensive data augmentation because as you can see on the right, there's not a lot of variation to the shape of the hand and to the background that the dataset uses. So we use color jitter to adjust the contrast, brightness, and hue of these images. We use random rotation to change the orientation by some small random angle. And we use random resize crop to simulate what the effect when your hand moves farther away or closer to the camera. Now, when we were choosing the architecture, we had two main objectives in mind. The first is to choose a model with low model complexity and specifically fast feed-forward runs, because we want to be just classifying on frames of a video in real time. So the faster the feed-forward, the better. And the second objective was to choose a model that would more easily generalize to this task, because as mentioned before, our main problem was this data set lacking variation. That's why we use convolutional filters that are pre-trained on ImageNet for this task, because the images in ImageNet include all kinds of colors, textures, and shapes. So these learned convolution filters should help us avoid overfitting. Now, it also helps with training speed because we won't be training all the filters from scratch. We use weights and biases to log our training. And what we found is that rather than doing a standard transfer learning where we freeze all the convolution filters during training, it was actually better to allow them to tune themselves a bit to the hand images, probably because this helps them specialize to detecting the specific shape of the fingers and palm. Now, one technique that MobileNet V2 uses to reduce the number of parameters is what's called a depth-wise separable convolution. Now, if you look at our standard convolution layer, we have these kernels that convolve across all the channels of the input image. They essentially collapse the input channels into one output channel, and in order to produce more output channels, we would need more of these K by K by C kernels. Now, on the other hand, a depth-wise separable convolution breaks down the convolution into two steps. The first is a per channel convolution, where you apply separate K by K kernels to each channel of the input image to produce this intermediate image of the same depth as your input. Then we use 1x1 convolutions to combine information across all channels of the intermediate image to produce the output image. And same as before, to have more output channels, we need more 1x1 convolutions. This already makes the advantage very apparent because now to have more output channels, we only need to make more of these 1x1 convolutions rather than the K by K. And this also drastically reduces how many multiplications we need to compute this convolution. And the other advantage is that now we're also adding more nonlinearity. We add an extra activation step at the 1x1 convolution.
Okay, cool. And so now Andre is going to try to get the live demo set up, which he's going to do from his live video camera. And in the meantime, I just want to go again through the results. So again, this is just to clarify, a fist means no, which you can see on the bottom left. A palm means I have a question. Naturally, people in high school, you raise your hand for a question. Okay, we thought like the perfect sign would be great for okay. And then when it comes to having a comment, we decided to just raise a finger, like I got something to say, 1 or 2 fingers. Away from keyboard, again, we just showed this so you can see what's happening, but pretty much this entire camera would be covered as I showed in the demo in the GIF that I had. And then last but not least, we have the peace sign. And the peace sign just, again, peace sign, goodbye, makes a waving icon, and that should work. So yeah, that's the end of our presentation. I want to thank Weights and Biases for having us on this podcast, and again, MLab. And Andre, are you ready?
Yep, I just need to turn off my virtual background.
Okay, sweet. I'll stop sharing.
No. So the first gesture is a fist, should be no. And okay is yes. Palm is a question. Then 1 finger up is comment. And a peace sign will be goodbye. Then when I move out of the frame, it should cover my screen with a graphic.
Okay.
When I come back, it should move away.
Yep.
That was our presentation. Thank you.
Yeah, thank you.
Great. Thanks so much, Andre and Ashwa. It's really impressive work that your team put together. And so I think it was a pretty short timeline as well. Can you say how long it took to develop that from concept to execution? Yeah,
that's a great question. I think we did start, I actually forgot. Semester has been quite a long semester, but I think we started around the beginning of November and spent about a month or so. One thing that was difficult, definitely the fact that like half of our team was PST and half of it was in like China and Singapore. So time zone differences, but we still, we made it work, and yeah, it was great.
Gotcha. Yeah, I imagine that's an experience a lot of teams are having in this year. I've been doing a lot of online teaching, and some of that has been on Europe time, on Indian and China time. So yeah, it's been a wild year for time zones. And yeah, impressive that you put that together in just a few weeks. I had a couple of questions. So one about you used a non-deep learning approach at the beginning for sort of selecting out your bounding box. And so I wanted to hear a little bit more about that sort of like, how'd you choose that particular Haar cascade approach? How'd you find it? What other options did you consider? And can you talk more about the decisions you made as in that part of the process?
Yeah, for sure. I guess I can take that one. So I guess in the beginning, yeah, when it came to hand face tracking, we initially, I think our team wanted to create our own from scratch. But then again, given the limited time frame, we decided to go off the shelf because the core of the project came from the ML side. But with that being said, in terms of alternatives, I definitely will admit that one of the hand tracking was amazing. I'll just admit that Victor Dubia did a great job. But when it came to face tracking, I think one of the downfalls of Haar Cascades is, as I talked about in the slide of the Haar features, like if you're wearing like sunglasses or maybe even a mask, which is common in this day and age, like it blocks your nose, your mouth, and your eyes, and that can actually be a downfall. So we thought like some other methods could be, I believe there's other things like dlib is something in C++ that can work. There's something called MTCNN. I forgot exactly what that stood for. And most importantly, I think YOLO v3 is used for self-driving cars for detecting different objects. And that's more deep learning based. And if it was deep learning based, we could train it so that you could make like a YOLO v3 version for like while wearing a mask or while wearing sunglasses. So it makes it more robust overall. So yeah.
I see. Was part of it also an attempt to sort of like cut down on the amount of computation? Like, is the Haar cascade applied to the whole image cheaper than doing something like YOLO v3, or has that advanced to the point where the computation difference isn't that big?
So I believe that we haven't exactly empirically tested the differences between, I guess, like YOLO versus Haar cascades. But I do believe Haar cascades is pretty fast. I personally have used it in the past, and it's definitely an old algorithm. I think CVPR 2001 was when Viola and Jones made the initial algorithm and proposal on the paper. So definitely we've come quite a far way. But yeah, I don't really know about whether it'd be faster. But for our purposes, it works. Or like, don't break something that doesn't, that keep something that works, I guess. Yeah.
Yeah, definitely. There's an appeal to the simplicity of something like Haar cascades. Yeah. It looks like somebody in the chat is suggesting multitask cascaded convolutional neural networks as a potential option.
Yes, yeah, sorry, MTCNN, that's what I meant to say. That was, yeah, that's one. Awesome. Yeah,
gotcha.
Thank you.
Okay, that's MTCNN. Cool. Yeah. I guess, what would you think, I don't know what your plans are with this particular project, but let's pretend that this was, a minimum viable product at a company. What do you think your next steps would be with this project? What do you think does it need in order to be able to scale or enable to be like usable in different domains? Like, what do you think you would do next?
I think it would be cool if, so now we have these few gestures that we had in mind when we were building this project, right? I think it would be cool to have a more general gesture recognizer that can perhaps learn to classify a particular gesture with just a few examples. So that way, different people using this application for different tasks, they can customize it to their own needs. So maybe they want to, their line of work needs a particular signal, and they could customize it for that.
Nice. So I also noticed it seems like the way you framed it, it's an image convolution image classification task. Did you think at all about how you might extend this to video?
Yeah, I had some idea about how to do it for video, but we didn't really have time to implement it. So I heard one way to do it is to have a CNN extract the features and then feed that into an RNN that takes different frames from the video, which then like takes the time series and then produces some temporary result.
Yeah, that's an interesting suggestion. Yeah, I think if you had the compute, transformer type architecture could probably handle something like that. But getting that to work during somebody's live Zoom presentation sounds like a really tough challenge. There's a question in the YouTube chat, just the last one here. They are looking for slides. Will you be able to share these slides? Do you mind if I share them on the video?
Yeah, most definitely. I can send you the link maybe after, and then we can make it public for all access. Yeah.
Great. Yeah, I'll put it on the video. Awesome. All right. So I'd love to be able to ask more questions of all of these groups, but we've got 3 different great presentations to talk about, so we've got to move on to the next one. So next up, we have a group that worked on semantic convolutions, on essentially alternatives to convolutional neural networks for computer vision tasks based, I believe, around capsule nets. So we'll be hearing from Domas and Kenny on this project. So go ahead, take it away.
Awesome. Thank you so much. Yeah, so we really explored the idea of semantic interpretation of convolutional networks. I'll ask you to the next slide. With our objective being vision networks are largely not super interpretable. And this is more of a research-based project than some of the other, the previous presentation. The intuition of hierarchical layers of progressively understanding more complicated features, you have an edge to a part detector to an object detector, doesn't really empirically work out in practice. You end up getting this big mess. Some of these undesirable properties, there's a whole laundry list here. We'll get into them more in detail, but an over-reliance on texture and a need for data augmentation, as you saw with the previous group, you have to show all different orientations of your hand and upside down and whatnot, ways in order for the network to really learn the full picture. Next slide. So here we have a single activated neuron in a sense to show how confused it can get. We have the same neuron looking at the eyes, the whiskers of a cat, the legs, and the fronts of a car. And so obviously, with the next slide, it's doing all 3 at once, which makes absolutely no sense. Hence our quest for semantic meaning. So CNNs are brittle. With the Statue of Liberty, you understand that it is the Statue of Liberty, whether you see it from the back, whether you see it at nighttime with different shades and textures and colors. But that's not quite obvious to the network, hence the need for data augmentation, and which really blows open gaping holes in modern architectures. We look to kind of biology for some motivation. Next slide, please. And the way that we do it is we reason in a set of invariant primitives. We don't think of objects in isolation. We think of them as things that are kind of detached from the orientation, right? And in actual brains, you have circuits that fire whenever the object in any orientation is present. If the cat is upside down, if it's backwards, if it's dark out, the same circuit fires for the cat. Next slide. And we do this by imposing geometric coordinate frames upon the object. So here's Jeffrey Hinton, the creator of the network we're going to show you. He walked around the halls of MIT with 2 blocks and asked professors to create a tetrahedron with those blocks. And none of these brilliant professors, leaders in their field, could do so, even though they're geniuses, because they think in terms of coordinate frames, they think in terms of geometry. And the blocks in isolation look like nothing that could form a tetrahedron, yet when you make the tetrahedron, it's obvious because you impose a coordinate frame, you impose geometry. Next slide. So the solution is Hinton's Capsule networks impose geometric structure on CNNs. So you learn object representations invariant to viewpoint. Your object does not depend on the way that you look at it, it just exists. Next slide. So empirically, these networks are very data efficient. You don't have to augment your data set. You look at an object once and you understand the way that it works. And because of this, it's also robust to adversarial attacks and shifts in the way that you present your input to your network. And there's less redundancy, and you get state-of-the-art performance with an order of magnitude less data. I'm going to turn over to Tomas to explain some of what we did.
All right, so here's a bit of an example of what some of the low-level feature maps look like in CNNs. And you can see that there's a lot of redundancy. There's a lot of these same frequency activations, which are just rotations of each other. And you see similar things in the color spaces as well. So that's something that we're trying to avoid with our usage of capsule networks. Okay, so the paper that we're re-implementing is stacked capsule autoencoders. And this architecture is a combination of 2 submodels, which is a part-capsule autoencoder and an object capsule autoencoder. The first model, it predicts parts and their poses. So the parts here are these different little bits that compose the house and tree and such. And these are the poses that are then predicted. Then the second part of the model predicts objects. So it associates each of these parts with an object. So it can find that this tree is composed of this leaf part as well as a bottom trunk part. Okay, so I'm going to go into a bit more detail on the Part-Capsule Autoencoder. So this is the first stage, which predicts the positions. It actually does this using a CNN, and it also uses a decoder, which learns templates. So in the forward pass of the encoder, you get these poses as well as some descriptive features about each of the parts, and these are reassembled in the decoder with these templates to produce a reconstruction. And this is optimized with the log likelihood loss. And here's some visualizations of what the composition looks like. So these are the learned templates or parts, which are then transformed and then concatenated together to form this reconstruction. And you can sort of track using this color coding how each thing sort of comes together to have this final result. And this is the reconstruction without the colorization. So you can see it's a very realistic looking tree. And you can interpret these templates that it learns as strokes. The transformations are like a strokes on canvas, and your final thing is the digit, of course. Okay, so during our experimentation, we studied the evolution of these different parts which are learned. So at the very start, it starts with this random noise initialization, then it gradually gets chiseled out into more meaningful parts. So here you can see roughly there's an edge. Here we have some double edges. Here we have a more flat looking edge. Then here we have a very circular object. Okay, and over time, we can see that at the very top, the transformations of each of these parts are pretty nonsensical and naive. It's totally random noise just getting warped around, but gradually they get positioned more and more sensibly. And as the templates at the same time are chiseled out, you end up with these very high quality reconstructions. So on the very left, on the left column, these are the target images, and the right are the reconstructions. You can see that they're reconstructed fairly faithfully. And at the very bottom, you can see the corresponding templates, which are being utilized for this last reconstruction. Okay, so the second part of the SCAE model is the object capsule autoencoder, which takes each of these poses of parts and also the feature information and tries to explain the sort of mess of parts. So it associates them with objects, learning the relative positioning of each of the parts in the object. And then using this model, we want to optimize the likelihood of what it sees. So in the final model, we train both autoencoders jointly to optimize a task for unsupervised object classification. Yeah, so empirically, the paper gets really good results on the MNIST and SVHN. There's still quite a bit of room for improvement, which is what we're trying to address with this project. So one of the issues is the engineering difficulty. Their original implementation was in TensorFlow, and it's quite messy because it's research quality code. So we ported that to PyTorch, and so far we finished the PCAE re-implementation, which you saw the results of earlier. And we're currently working on the OCE re-implementation. We're also working on other improvements, such as reducing the training time of the OCE, as well as improving the depth of the network. So we want to be able to stack multiple OCAEs after the network so that we can get more rich compositionality in our network structure. We also did quite a bit of hyperparameter tuning, and we found quite a few interesting key engineering decisions that the paper doesn't really talk much about. Yeah, so this is the work we did. Re-implementation, hyperparams, found some interesting factors. We also did some experiments on USPS, which is very much like MNIST, but it's a bit different stylistically. So we verified that it works there. And we're also working on extending reconstructions to color images. They never do anything with color in their work. Okay, so Kenny also did some optimizations, so I'll let him explain this.
Yeah, so basically the loss is driven by a closed form log likelihood that's evaluating the efficacy of capsules and routing their parts to the correct capsule, which is a very complicated equation. And as you can see, when calculated in closed form, is a considerable amount of computation. We can leverage a technique called Markov chain Monte Carlo simulation to sample from this distribution and kind of create an approximate distribution from which we can then pick off the peak of the distribution, the maximum a posteriori, the map, if you will, to route our capsule to the part from our sample distribution such that we can use less computation. This is one of the things we're exploring. We're also exploring using just an argmax value to drive loss in the backpropagation instead of a closed form log likelihood, which we speculate, and we have synthetic preliminary data to show it's not entirely necessary, and it would save a lot of time in training.
All right, so some future work that we're looking to do is finishing up our PyTorch port. And we have some big ideas which we're shooting for. So one is the RGB dataset performance. Hopefully we can get this the speed up to work on the actual OCE model. We also want to add more capsule layers so that we can scale to more complex data sets, like for object classification in ImageNet or CIFAR. And we also want to modernize the PCAE CNN. Right now it's a very simple, small CNN architecture. So yeah, that's all. Any questions?
I've got a lot of questions, so we'll try and squeeze as many of them as we can in the minutes that we have. So you mentioned that it was hard to train because it had strange loss dynamics. Could you unpack that a little bit?
Yeah, maybe I'll talk about the
Sure.
the actual
Absolutely.
strain of the computation, and Tomas can talk about some of the dynamics of pairing the encoder likelihoods. So like the likelihood itself is a very, it's a closed form distribution that you have to calculate with each forward pass in closed form, and then derive the argmax from that value or from that distribution each time. In a sense, it's just a cumbersome way. You can't leverage sort of automatic differentiation techniques to do things speedily. Was the problem we ran into. And then Tomas also ran into some issues with the PCAE.
Yeah, so what we spent the most time on tuning the PCAE is actually getting a nice balance between the chiseling of these templates. So some extremes that we had to sort of dig ourselves out of is one, in some cases the templates weren't actually in frame, so it never like quite latched on and started training the model to actually make usage of each of these templates. So they ended up just being totally unused in some cases. In other cases, we had way too much transformation and had really weird transform parts. Like we had super zoomed in templates, which had some interesting behaviors. Another one was, we just didn't have any transformation going on. So there's a very fine balance to strike in between those two.
I see. Do you think that just it's a matter of picking the right sort of hyperparameters and defaults to make these capsule nets a little bit behave a little bit better during training? The way that we've sort of come across the right ways to initialize layers using things like batch norm, et cetera, to make confnets easy to train? Or do you think that it's inherently just going to be harder to train something like a capsule net than something like a feed forward regular convolutional net?
So we found that actually after we made one key discovery, which is that we want to learn the transformations or the transformations outputted by our CNN need to be in inverse space. So basically, we output some 3x3 transformation matrix, we invert that, and then use that. And basically what that means is you can think of it as the space which you're optimizing over has a totally different morph to it. So it's going to be expanded in some regions and shrunk on some other regions. So because of that, you get a much better loss surface to optimize over, and everything just starts magically working.
And to also answer your question in terms of like tooling, I think some things will need to change a little bit, right? You're not building these vector Jacobian product type computations. You're really looking at this likelihood, and there's going to need some more well-defined computational building blocks to make that happen. We're going to pursue sampling to see if we can get an approximate answer to that question, especially because we don't have to be super specific when we generate this distribution over like capsules which are good. We don't need to be very specific over the region where the map is. We can kind of like be in a general area to route the correct capsule. So that suggests that this could work. But there are other things we need to look at as well.
I see. Yeah. To Damas's point, I know that in other domains, actually sampling, it's the parameterization. It's very well known that the parameterization of your model is very important, and there are tricks like taking inverses and taking logarithms that help a lot in getting a well-conditioned loss surface. So it could be, yeah, that those are the kinds of things that need to be discovered. And to your point, yeah, there's a lot more tooling that could be built for for probabilistic programming and for differentiable probabilistic programming that could probably unlock a lot more capacity in things like capsule nets that might marry those two approaches.
Yeah, like we were just using the PyMC3 Bayesian stat package, which had no sort of fine-tuned computational optimization. We still got decent results with synthetic data. So some room for improvement there.
Definitely. There's a question in the chat. Testing semantic correctness can be via saliency on expected inputs, like on MNIST. The difference between digits 5 and 6, see that the circle of the 6 is complete or not. Have you looked into this? I guess they're asking, you mentioned that you wanted to make confidence more interpretable. Have you looked at the behavior of your capsule net to see if it is more interpretable, if you see these sorts of semantic distinctions like they're talking about?
So we haven't used any of the techniques which are standard for CNNs. In fact, in our surveys, we actually found that there's a good amount of controversy as to what these visualizations are actually doing. So we wanted to try and move away from these post hoc attempts to understand what's happening so that we can build the understanding into the network. So it's what the network is doing is clear from the structure of the network. You don't have to do any inspection afterwards.
I see. That's an interesting point. And that actually brings me to the last question, or one of the major questions that I had, which is also a tough question. The vibe in the ML community over the last year has shifted really heavily away from inductive bias with the success of transformer models on multiple domains where they don't have necessarily a super great inductive bias, and that it's which sparked, I believe, Richard Sutton's famous post, The Bitter Lesson, that in the end, scaling compute tends to beat out these architectures with special things built into them. So I'm curious, do you think that's a fad, or how do you think that this taste for transformers and generic architectures broadly dovetails with your particular interest in these more biased structured architectures?
I think there's a lot of parallel. I think these are almost the same thing. At least they're converging towards the same approach. Attention mechanisms are taking permutation invariant sets of objects and deriving importance that are, irrespective of how far away those things are apart from each other. The same essential mechanisms happening when a capsule is voting on a part. And in fact, the architecture, it draws a lot of similarities with hierarchical temporal models, or those Bayesian inference type models that are biologically inspired. All three of them seem to be converging towards that general trend of attention. And I think that's where this is all going.
Another counterpoint is that models with really good bias typically have better data efficiency. So this was actually shown in capsules. They're actually an order of magnitude better than other typical approaches to MNIST classification.
That's a good point. And to Kenny's point, so the research group that I worked at when I was a grad student at Berkeley, the Redwood Center for Theoretical Neuroscience, is very interested in a lot of the ideas that you've mentioned: dynamic routing, hierarchical temporal memory. It was originally created by Jeff Hawkins of Numenta. So if you haven't swung by the Redwood Center's Zoom meetings, you definitely should email me afterwards if you want to hear more about that. That's a good point. That the attention mechanism there is very, very similar.
It's all about invariance. I mean, that's what Hawkins talks about in his book, right? That's the key to biological interpretation, is learning invariant representation of objects. That's what all these things are doing.
Mm-hmm. Neat. All right. Well, that is all the time that we have. So we'll have to continue that interesting conversation on a later date. So thanks to Kenny and Damas and their team for presenting that cool work on capsule nets. And let's go to our final set of speakers. So we'll have, so we just had Damas and Kenny, and now we have, I believe, Pedro and Oliver, who will be presenting their work with on adversarial attacks. Also a little bit more research oriented than our first video gesture overlay, but maybe sort of in the intersection of what's of interest to researchers and what's of interest to folks doing ML engineering. So Oliver and Pedro, take it away.
Thank you. Let me share screens. Okay, so my name is Oliver, and this semester we have been, my team and I, me, Vincent, Nabil, and Pedro, have been working with Nicholas Carlini on attacking adversarial defenses. And I know that's very general if you know anything about the field. And so we're trying to own in on a specific type of defense and try and come up with a more general attack framework so that we can have a better metric in a lot of these papers, because some of these defenses claim to work really well, but they don't actually attack themselves very well because you know, that doesn't really help their claims. And we really want a better, more principled way to attack these defenses. So first, some preliminaries. So in case you don't know, an adversarial attack on a neural network is a perturbation of some input, which causes the network to misclassify the input. So in this image at the bottom, you have all of these inputs and the line is splitting them up well. And then if you allow some perturbations, you allow them to move around, then you can get misclassifications. And then we make sure that the constraint, or we make sure there's a constraint so that the perturbation isn't too big, so the original images don't get too far away. And this is a really big vulnerability in safety critical fields. For example, self-driving cars, because you can have things like hiding a stop sign from the computer vision model of the car. And that's really, really dangerous in such a safety critical field. So defending against these kinds of attacks is really important. So here is a sample attack, just a really simple example that's used for a lot of just like prototyping. It's called the fast gradient sign method. And what you're doing is you take the image, and then instead of doing gradient descent on the parameters of a neural network like you'd normally do when training it, you do gradient descent on the image itself. So you take the gradient with respect to the image and you add that instead. And what this does is it forces your loss to increase when you add this perturbation. And so as you can see in this example, we take the original image, we add a bunch of what looks like random noise, but it's actually specifically selected to attack this model. And it doesn't look like the image has changed at all, but it completely changes the classification and increases the confidence drastically. And this is really dangerous. And so finally, here is an example defense, which was proposed in Madry 2017, which is one of the most important papers in this field, where you can use FGSM or some other similar attacks and use it as like a form of data augmentation during the training, where you do your normal training, and then in the middle, you take some examples, you take your batch that you're training on, and then you get some adversary, you attack them while you're training using the current model, and then you pass those in as more training examples. And then you hope that this makes your model more robust and gives you like a more nonlinear surface like this that fits the perturbations better. And then now I'm going to pass it off to Pedro.
Okay, so now that we see why having adversarial robustness is important, let's talk about why it's hard to do. So looking at this from the attacker's perspective, we see that all they really have to do is to maximize this equation, which really means that they have to maximize the loss, adding some perturbation onto the original image, the loss compared to some truth value. And so we have this loss being very high and the perturbation being very small or within some bound. And the first perspective here is that it's hard to construct a theoretical model of what the attacker is doing and how they actually create these adversarial examples. This optimization problem is nonlinear and non-convex, so it's hard to generalize overall to see how different attackers make these adversarial examples. The second perspective is that adversarial robustness, which means just protecting yourself against adversarial attacks, requires models to have good outputs for all inputs. And it's pretty easy for an attacker to make an adversarial attack, but it's very hard for a defender to defend against all possible adversarial attacks. And here we have an example of adversarial detection. What this is what if we could have a layer that before we input anything into our model, we have a layer that tells you that, yes, this is an adversarial attack, or no, this is a good piece of input that we want to continue with. And so this picture shows just a layer in between the adversarial example and the actual model that will tell us that information. And the problem with this is that some models are not able to ignore this input. And so what this layer would do is, if it's good, pass it on. If it's bad, throw it away. But if we go back to the self-driving car example, the self-driving cars can't throw away an image. They have to make a decision. If they see a stop sign, they can't believe that it's adversarial and just do nothing about it. And so talking about some very rudimentary defenses, the idea here is that what if we have in between our adversarial example and our actual model, a layer that pre-processes the image. So this is not exactly throwing away the image. This is just pre-processing it, throwing it through some function. And in this case, we'll look at the Gaussian blur. The idea is just to blur the image, a normal Gaussian blur. And the intuition is that what if we can smooth out the high frequency noise, and we can hope that the adversarial component of the input is in that noise. And we can smooth that out and essentially throw only the adversarial noise away. It turns out that this is not a very good idea, and we can actually attack this very easily. And the idea here is just we have to fool both the original model and the defended model. If we try and fool any of them individually, let's say we have the defended model, which has that Gaussian blur preprocess step. If we defend that, we might produce adversarial examples that the original model cannot produce good outputs for. And so we want to attack both the original model and the defended model, and we can chop this together just using a linear combination on the losses and take the gradients with respect to their inputs, and then produce adversarial examples that work for both the original and the defended model. A defense that's a little more complicated uses ensemble methods. And the idea behind the ensemble is just that, okay, you have an input. I'm going to give it to, in this picture, 4 different models. And the models are going to produce some output and vote on the output or have some average of the output. So the actual ensemble prediction will be some function of the outputs of those models. And in this case, we can have 2 different types of models. The first is the full precision model, which gives high accuracy but low robustness. And the second is the low precision model, which has high robustness and low accuracy. The high robustness factor of the low precision model comes from quantization. And when I say quantization, I just mean chopping off some of the bits of the input so that essentially we're taking away some of the lower precision parts of the image. And the idea is that what if we can get the best of both worlds? We want the high accuracy and the high robustness of the models. And that's the idea behind the ensemble method. It turns out that this does boost adversarial accuracy by about 15.3%, but we'll talk about why it doesn't quite work as well as we wanted to on the next slide. We can attack this. The insight here is that this defense just masks the gradient signal. It doesn't actually really increase the robustness. A big consequence of ensembles is that it masks the gradient because it uses several different models that either vote or average on an output. And so what we found was that the full precision models have a very, very similar loss surface to the loss surface of the entire ensemble. And because this is the case, the gradients are not very well hidden. We can just retrieve them by using the full precision model. And so what we do is we just take the gradients from the full precision model, find some adversarial example using methods that are already known, like FGSM or PGD, and then we can plug this in through the actual entire ensemble, and this works a majority of the time.
Okay, and then a second paper that we've been working on is there's another proposed defense which seems quite different from the last one. It does use ensembles as well, but the mechanisms underneath, rather than doing quantization to increase robustness, is they use some work from error correction codes. So they try to use error correcting codes to increase the robustness. And so the key insight is that when you do adversarial perturbations for a neural network, you are you're taking your inputs and then you're perturbing it, and then you're trying to change the outputs. And so when you have the one-hot encoding like you would normally do, all that you have to do is change a single bit to get a new output, right? If you have 1, 0, 0, all you have to do is change that to 0, 1, 0, and that technically just requires changing 2 bits. You reduce the 1 to a 0, and then you increase the 0 to a 1. And so that's called the Hamming distance between those 2 bit codes. And what error correcting codes do is they let you have a larger Hamming distance between these encodings for the outputs. And what they do is they design a codebook that, instead of using the identity function, which is the one-hot encoding code word, where you have just 1000, 0100, etc. You use more complicated code words here. And so here's some pictures from the paper, where on the left is the original models just without this new loss. And it's pretty easy to go from low probabilities for a class to high probabilities for a different class. Like, you just have to cross this little boundary in the middle here. But in the middle one, it's much harder to get from something in the red side, and you take like some harder traversal through the green, and then you get to the blue. And so it makes it so that your model is more robust and it's harder to change codes. And so in practice, they use Hadamard codes. And so this is an example. Instead of using the identity matrix and one-hot encoding, you use these codes that have a larger Hamming distance between them. And so it makes it harder to flip the bits, and it makes it harder to perturb the inputs. To give a fake example. And then for the loss that they use is you just take some sigmoid, some increasing function bounded between 0, 1 of the outputs of the neural network, and then you do the dot product of that with the corresponding row for whatever class this is an example of. And then you do like a softmax like loss, where you end up getting a probability out of this, and then you maximize this loss over the average over the batch. And so this gives you actually probability, and it turns out that this paper, in addition to improving robustness, also increases the probability estimates, because a lot of neural networks, they output the probability of it being a class, but lots of times we just ignore that and think, oh, it is this class or it isn't this class. But it turns out that this can give you more robust probability estimates as well. And then finally, they also just throw in an ensemble for the same reason as the EMPIR model, because it'll just increase the effective Hamming distance between all of the codes. If we have lots of different codes at the same time being like working together to vote on a single output. So when you're training these, each classifier has different parameters. They don't share parameters, and then they're just solving a different classification problem because you have different encodings of the outputs. And then finally, we were trying to attack this paper and show that it didn't really work as well as they claimed. And the reason that we knew that it wouldn't work as well as they claimed is because if you look at this graph here, the two outputs that are kind of their state-of-the-art methods are the green and the blue, the light blue over here. And if you look at epsilon 0.5, they claim that their accuracy is around 40 to 50% for an epsilon value of 0.5, which is the bounds for our perturbations. But at this bound level, our images, our pixels are mapped between 0 and 1. And so if you think about it, if you have an epsilon of 0.5, you can turn any image into just complete grayscale and just take any image and convert it to all 0.5 for every pixel value in the image. And that fits within the bounds of this perturbation, which means that's a valid perturbation for this value. Like that's a valid attack for this constraint. But if you get that and there's 10 classes and every image is exactly the same grayscale image, there's no way you could get above 10% accuracy. Yet they report 40 to 50% accuracy. So something is not working properly with their model, or they're not attacking it properly, which was kind of suspicious. And so similar to the EMPIR defense, we noticed that the error correcting code defense here was performing gradient masking. And the way that we realized this was in this loss function here, you realize that they take some sigmoid function, and in the actual code, when you look at this, they take the log of this. They take a log in the loss somewhere. And after they take this log, it causes the gradients to get really, really, really small. And it causes like a vanishing gradient issue. And so in effect, what that does is it just masks the gradients similar to before, where it makes the gradients really hard to read and there's not very much information from them because of that. But what you can do is you just take a similar model where you get like a smooth approximation of the gradients and you get rid of this vanishing gradient problem. And it's not the exact same model, but it's pretty accurate and almost exactly the same, just without the masking gradients. And then you just attack that instead and use those attacks for the new model. And what that does is it reduces the accuracy already from 50% to 15%. And that was the first thing we noticed, and we're still working on this, but it was a pretty drastic improvement already from even the claims in the paper. And so that's a general theme with a lot of these papers, is that they claim that they work very, very well. And then you try to attack them using stronger attacks, and they don't work as well as they originally claimed. And it seems like they didn't put in all of their effort to doing the attacks, which makes sense because their focus is the defense. But it's not really a valid claim that their defense works amazingly if we can attack it by putting in a little bit more effort. And so the goal is to generalize these attacks that we've been doing. There are some similarities. We plan to generalize these attacks to a larger class of defenses, and so that we can find the commonalities between the errors in a lot of these defenses and figure out a more principled way to attack them. And in particular, we really want to focus on the class of detection defenses that Pedro mentioned at the beginning, where you try to either discard or not discard images based on whether it's an adversarial example or not. And so that's what we're going to be shifting to soon, now that we have a good amount of practice attacking some defenses. So yeah, and now if anybody has any questions.
Great. Yeah, I've got a lot of questions. I think I'm going to start off with one that's closer to a comment, but I'm hoping to spark a discussion. So you mentioned that the error correcting code approach gives you better calibrated outputs in terms of the class probabilities. Mm-hmm. One thing I've noticed when I've done work on adversarial attacks and defenses is that people's baselines tend to be really badly calibrated, because the default of a neural network is to be badly calibrated. Those class probabilities that you get out on held out data are not good. If it says it's 0.1, that it's some other digit or some other class, it's actually maybe more like 25 or 30% probability. Mm-hmm. And so there are ways to fix that. And what I found is that if you just make a model that's a little bit better calibrated, your adversarial defense, like you actually become slightly more adversarially robust. And so it's very easy when you're just designing a defense to accidentally just calibrate your model better. And then in the process, that makes it look like you've come up with a new way to become to have a better defense. I'm curious, I guess, to turn that into a question. Did you notice anything like that when you were looking at all the different defenses and superior attacks that in your review of the literature and the work you did?
So I can ask Pedro if he noticed anything for the EMPIR, but it seems like something like that is going on here, because we know how to attack lots of models at the moment. There's lots of defenses that have been published, and Carlini has been instrumental in attacking lots of them. And what happens in this one is they claim to work really well, but it clearly doesn't. So my guess is that for our model, there is something like that going on. Like the effect of this paper is just that it gives you better calibration. And then they throw lots of theory in there. And in effect, it's really just improving the calibration. And then as a result, it gives you a little bit better robustness, but then you just have to fiddle with a little bit of the attack parameters, and then you can get it to work. I'm not sure if you noticed anything like that as well, Pedro.
Yes, so I think that's really a major theme. We're seeing a lot of these papers from, iClear and Europe's being broken very easily because all they do is mask gradients. And really what they try to do, they focus on making it hard to retrieve these gradients so that we cannot run FGSM or PGD or other attacks on them. But they're not really making it more robust, they're just making it harder to get those gradients. And the problem with that is that they can laser focus on, here's a model that is hard to get gradients from, but we can just build a substitute model that is on our own accord, has our own rules, that has smooth gradients that we can attack ourselves. And those adversarial examples that come out of those attacks from models we build that are similar to the models that are claimed to be robust, we can just transfer those over and they work a majority of the time.
Mm. On that front, I guess, what do you think could be done to make research in adversarial attacks and defenses better to avoid this problem? Do you think that there are some sort of institutional changes that could be done that could help this? Or is it just, we just have to learn to do better when we do this research?
I think it's kind of hard. Maybe there is institutional stuff you could do. I'm not sure. But I think the issue is that a lot of these attacks are very specifically tailored to every single defense. And so what happens is people take some general attack that is just very general, and you have to tailor it a lot. And, maybe for these examples, right, they do gradient masking. And so we have to do lots of stuff to do, for example, FGSM. We would do FGSM on a different model and then use those attacks. And you have to tailor it a lot to every specific defense. And a lot of the defenses simply just take the attack out of the box and apply it. and say this doesn't work, and this is like the strongest attack that exists, therefore our model works really well. And they don't really put in the amount of effort that they should to like attack their model really, really hard. And I guess it makes sense from their perspective, right? If they spend a couple months working on this defense, and then you spend a couple months attacking it, and then you actually attack it, then all of your time is wasted, and people don't really post negative results as often. Maybe that's an issue with the field as a whole, but negative results aren't as popular to post. And so it seems like if you did that kind of thing, then there would be a lot less defense papers, and so they just end up not attacking them as well as they should. And so that's kind of one of our goals, is that we want to be able to have a more principled way to attack these methods. And if we do come up with something like that, then a lot of the claims that these defenses can make, if they do claim to be defendable, or if they do claim to be able to defend such a principled attack, we would hope that that would improve the field as a whole, and it makes these attacks, it makes their claims much more accurate when they say that we are actually robust.
Mm-hmm. Yeah, I suppose in other scientific fields, there's a lot more peer review and a lot more rigorous peer review than in ML, which has brought its benefits and its drawbacks. And perhaps one of the drawbacks is that it's easier to get a paper published that hasn't been subjected to a rigorous enough attempt to counterclaim.
Yeah, but I guess, we still do see the scientific method happening, right? People post a defense, and then Carlini comes and attacks it. And so that's the peer review in action, I guess.
Mm-hmm. Mm-hmm. Yeah, it's slower, or maybe not even slower. It's just public instead of private, which is maybe
good.
Great. That's it's really great to see the work that you've done and that everybody at MLab was able to do in this semester. Really impressive, the amount of work that you're able to get done. And so I'm looking forward to seeing more from you all, both as you stay at MLab and as you move on to become ML engineers and researchers and members of full members of the field. Very exciting.
Thank you.
Thank you.
All right. So thanks to everybody who came and talked about their work. Really great discussions. Thanks to folks who asked questions in the chat as well. And I will see you all next year at the next Weights and Biases Salon. All right. Take care.